attributes. So the quality of global city is assessed. Uh, uh, wait, uh, so the quality of global city is help the economic, social, cultural, and environment attributes to improve the city and manage their to manage their influence in international finance. And the quality of global city is a key player in the other country which will be connected and the law. That is the cost of global ratio. This is roundings. This is the volume of global index. Global city index starting was not the global spot, but are consistent the valuation factors allowance export profit. First, to help the young growth. Some of the small business being successful on big mass stocks or stockouts. One of the example now, stock market firms like either stock or the extent everything about the stock probably seems Steve Marshall or three of us. Last year, technologies and bonds, CNN, thanks, easy problem, because we video, their points, subjects, easy for tech and innovation. Big tech problems now also some of the big tech problems now developers have a little bit average. Thanks, man. Thanks, we don't know about balance, and further out of the state. We mentioned powerhouse, economics, global economic law, plus one figure, plus coordinated universities, and profit share responsibility. Always called that. We have those recyclable. See, they were like deep and well. Hey everyone, welcome back, and let's write some more neat code today. Today let's solve minimum cost climbing stairs, and this problem is very similar to another problem that we've solved that's called climbing stairs. And honestly, I think this is probably one of my best videos explaining dynamic programming. I really walk through all the steps from recursion to memoization to dynamic programming. So I will link this video somewhere on the screen or somewhere on the description if you want to take a look. It's very similar to the problem that we're solving right now, which is minimum cost climbing stairs. It's just a slight variation of that other problem. So we're given an integer array called cost, where cost of I is the ith step on the staircase. And if we pay that cost at index I, then we can either climb one step or 2 steps from index I. So in this example over here, we're given an array of 10, 15, and 20. What we're told is that if we pay this cost, if we're at this position, right, and we pay the cost of 10 from this position, we can either take 1 step, which will land us in this position, or we can take 2 steps, which will land us in this position, and we only have to pay a cost of 10 to do that. And also, we are told that we can actually either start at index 0 or start at index 1. So we can either start from this position or we can start from this position. And our goal is to reach the top floor of this staircase. So you're probably thinking, okay, let's just start at position index 0, right? Take a jump of 2, which costs 10, right? Because we're taking 2 steps starting from here. So that costs 10. Then we reach this spot and then we're done, right? We've reached the top floor. So therefore the answer is 10, right? Well, not quite, and it's kind of tricky. I think it's really their fault that they word this problem kind of poorly. In this case, the answer is actually 15. Why is it 15? Well, it's pretty simple. It's because this is the last position in our cost array, but this is not the top floor. The position right after that is considered the top floor, which, yeah, they don't really specify that anywhere in the description, which is kind of dumb, but that's the thing. So the reason why the answer is 15 is because, remember, we can either start at this index or we can start at this index. If we start here, then we can take a jump of 2, which will land us at the top of the staircase. It only costs us 15 to do that. Or we could start at 10, take a jump of 2, and then take a jump of 1, which would cost us 30. Or we could Hey everyone, welcome back, and let's write some more neat code today. Today let's solve minimum cost climbing stairs, and this problem is very similar to another problem that we've solved that's called climbing stairs. And honestly, I think this is probably one of my best videos. It costs us 15 to do that, or we'd have to either take 1 step or out of bounds, and that's when we know we've reached the goal and we can stop. So initially we've noticed that from every spot we have 2 decisions, right? Take a jump of 1 or take a jump of 2, and we can't just be greedy and take a 2 jump every single time. So let's try every single possibility. And if you've watched any of my videos, you know that we like to do decision trees when we're brute forcing. So suppose we start here. We start at index 0 and we have, 0, 1, 2 to this index, and this index is out of bounds, and that's when we know we've reached the goal and we can stop. So initially we start at 0, right? We can either jump to index 1 or index 2, and the cost if we jumped to index 1 would be 10. The cost if we jumped to index 2 would also be 10. Now, if from index 1, we can either jump once, right, meaning we jump to index 2, or we can do a double jump and jump to index 3. Of course, if we're at index 1, the cost to jump from there is going to be 15, whether we take a 1 jump or if we take a double jump. From index 2, we actually only have 1 choice. We can take a single jump, which will land us at index 3, which is actually out of bounds. If we take a double jump, we'll get to index 4, which doesn't really make any sense because that's also out of bounds. So in this case, the cost from jumping from index 2 is 20, so we can put that. Now, just so you know, once we reach index 3, which we already have done in 2 of our paths, as you can see, we can't really go any farther from here. Right? So what we're going to say is, as we've stopped here, we want to know, okay, we reached the end, right? We want to know what was the minimum cost to reach this position. So one path, if we jump like this, the cost was 10 plus 15, which is 25, right? That's the total cost to reach this. Taking this path, it was 10 plus 20, which is larger. It took 30 to reach this spot. But we're not quite done yet. We know we can't go in this direction. So back to the actual description, the answer to this problem was actually 15. So why didn't we end up with the correct answer? And it's pretty simple, because remember, we were allowed to start at index 0 or allowed to start at index 1. But clearly in this decision tree, we started at index 0. So don't we have to draw another entire decision tree starting at index 1? Well, if you're clever and you take a look at this picture, starting from index 1, don't we already have that entire decision tree? Just look over here, right? We started at index 1 here. Now we did do some work before we got to index 1, but can't we just pretend like that doesn't exist? Can't we just reuse this entire decision tree? Obviously, we'd have to modify the numbers a tiny bit, right? Because when we start from here, the cost so far is not 10, it's actually 0, because we're pretending like we actually started from here, right? And that will be easy to handle for us if we recursively implement this solution. So what I'm saying is, for us, if we started at 1, we'd put a path over here on the right and then get to 3, and the cost for that would be 15, not 25 as we have down here. And the other path where we go left, we go jump to position 2 and then jump to position 3, that would cost us 15 plus 20, which means the total would be 35 rather than 45, right? So not 45 over here, it would actually be 35. The main point of what I'm trying to show you is there's repeated work here, right? If we take this solution as it is, it's exponential because it's a decision tree. Each node is going to have 2 branches, right? Up to 2 branches. And we're going to keep doing that until we get to the base case, right? Which is index 3. So what's the possible height, the max height of this tree? Well, we could have a potential level for every single position in the input array, right? So the height of the tree is going to be n, which is equal to the length of the cost array, right? So n is equal to the length of the cost array, and we know that we could have 2 branches for every single node, so the time complexity comes to 2 to the power of n. But as we just showed, there's a lot of repeated work that we're doing. If we eliminate that repeated work, we can actually get this time complexity down to big O of n. Because what we're noticing is, to solve the original problem, which is what's the minimum cost if we start at index 0 to reach index 3. To solve this problem, we're asking a couple more questions. We're basically solving the subproblem. We're asking, okay, how about to solve this problem, we have to first figure out, if we're starting at index 1, what's the minimum cost of reaching index 3? And to solve this problem, we're asking another subproblem down here. Okay, what about if we start at index 2, then what's the minimum cost to arrive at index 3? So if we cache this repeated work with a hash map or something, so that we don't repeat the same problem multiple times. What I'm saying is, over here, you can see that we start at index 2 and we want to know what's the cost to reach index 3. Well, it turns out that it was 20, right? From 2 to get to 3, it costs 20. So then, when we're trying to solve that same subproblem over here, starting at index 2, how much does it cost to get to index 3? Well, it was 20. We don't actually have to run through that because we already solved that problem over here. Right, so that's the main idea of how we can get this to big O of n. The reason it's big O of n is because we have n subproblems. We're asking, okay, from index 0, how long does it take to get to 3? From index 1, how long does it take to get to 3? From index 2, how long does it take to get to 3? So that will be an O of 1 operation for each position in the array, which will be n time complexity. It'll also be O of n memory complexity. And if we take this idea of caching the recursive solution, we can actually get an iterative solution that I'm going to show you now, which will have the same time complexity and, pretty much the same memory complexity as well. So now let's actually go over the real dynamic programming solution, which will actually have a slightly better memory complexity because we can actually use the input array itself that we're given. And we could actually even just use two single variables to do the DP solution. Let me show you why. So we noticed that to solve the original problem, right, starting from index 0, what's the minimum cost to reach the out of bounds position or the top of the staircase? We first have to solve the subproblem of starting from 1 and starting from 2, right? So basically this has a dependency of this and this, but we also learned that this has a dependency of this and this, and basically every one of these cells has that dependency. So how about we actually solve this problem from right to left rather than from left to right? Let's solve the subproblems first and then solve the original problem. Okay, so does that mean we're going to start from index 2? We want to know what's the cost for this to reach index 3? Well, it has two choices. It can do one jump or two jumps. The second jump doesn't do anything because it also goes out of bounds, right? The first jump will go out of bounds, so that's enough for us. And what's the cost to reach 3? Well, it's going to be just 20. Yes, that works, so we can just leave 20 here, right? So from index 2 to reach out of bounds, it takes 20. But what about from index 1? Now we kind of get into one of the more interesting cases, right? From here, we can also do a single jump. So then we're asking, okay, if we do a single jump, it'll obviously cost us 15 to do that single jump, but also the value that should be in this position is from index 2, how long does it take to reach index 3? Because then what we can say is, okay, for index 1 to reach index 3, we can just take 15, which was this jump, and then 20, which was the remainder, right? The remainder to reach index 3. So we can, in this position, we can put 15 plus 20. But hold on, because there's actually two paths, right? We already handled the single jump case, but what if we do a double jump from index 1? Then what's the cost that we'd put here? Well, we'd put 15 because that's the cost of making the double jump, but then we'd want to also add the value that goes here to that total result, right? Because from index 3, how long does it take to reach index 3? It's kind of a weird question logically to actually ask, but just to make the math work out, the easiest number we can put here is 0, right? Because if we're already at index 3, it obviously doesn't cost anything to stay here. So that's the reason why we're putting a default value here of 0. Now we actually have to look at two choices, right? Because one possibility was we go here, make a single jump to 2, and then go to 3, right? The cost of that will be 15 plus 20. Another possibility is we start here and then just do a double jump to this position, right? And the cost for that is going to be 15 plus 0 because there's a 0 here. So we want to take the minimum of both of these values. What's smaller, 35 or 15? Of course, 15 is smaller, so we're going to put the minimum of these two computations in. So that's what we're going to do to this input array. We're just going to append a 0 value to it. And then we want to iterate through this array in reverse order, right? So what index are we going to start at? Well, in the drawing, I started at this index. But remember, what we're going to be doing is taking this and then looking at the next two values that come after it. Of course, so really doing is just iterate plus 1, right? Because from here, if at the end of the array just to make the math work out easily for us. So that's what we're going to do to this input array. We're just going to append a 0 value to it. And then we want to iterate through this array in reverse order, right? So what index are we going to start at? Well, in the drawing, I started at this index. But remember, what we're going to be doing is taking this and then looking at the next two values that come after it. Of course, for the last index, or this index that I'm showing, there aren't two values that come after it. So we should actually start at this index, and that makes sense for us because we're not actually going to be updating this value because we're just going to take 20, add it with 0, which doesn't change this value at all, right? So that's why we're going to be starting at this index. How we can get this index is basically the entire length of the array. We know that the entire length of the array minus 1 will give us the last position, right? Length minus 1 will give us this position. So really, we can do length minus 3, which will give us this position, which is where we want to actually start at. So we're going to do the length of the cost array minus 3. And this is just how you do it in Python, at least with a for loop. And we're going to decrement We're going to keep going all the way until we reach the beginning of the array, and we're going to decrement by 1 each time. If you're not familiar with Python, all we reach the beginning of the array, and we're going to decrement by 1 each time. If you're not familiar with Python, all we're doing is just iterating, starting at this position in reverse order from this array. So remember what we want to do for cost at index I. What we want to assign this to is really the minimum of cost of index I plus cost of index I plus 1, right? Because from here, if we make a single jump, we're going to land here. So we want to add the value at that position that we land at to the original position. The second choice is if we make a double jump. So I'm just going to copy and paste this because it's pretty similar. If we make a double jump, this is what the computation will be like: cost of I plus cost of I plus 2. But if you want to actually simplify this line of code, you can see that since both of these computations have cost of I as the first value, we can actually just remove cost of I from both of these and actually just take the minimum of these two and add it to the original value. So we can just change this line to this, right? Take the minimum of these two and add it to cost of I. Yeah, that's the entire code. Just iterate through it in reverse order, do the computation, and then the only thing you have to return is the minimum of the first two values of cost of I, so cost of 0
It changes in complications at a global scale. What it means is that it's not just studying the combination of a specific country or city, but rather sakop niya yung certain parts of the world. So like, for example, is knowing like for example, is knowing the total percentage of male and female in a certain continent, knowing its birth rates or population growth, etc. So, ayun nga, hindi lang siya, hindi lang siya parang box sa isang topic. Instead, it covers a big portion of the world. So, kaya siya tinawag na global demography. Importance of global demography. Global demography provides insights into how populations change over time and how these changes impact various aspects of climate, economics, and environment. Basically, global demography uh, helps us better understand the patterns and changes of the world. So, knowing our global demographics, kaya natin siyang i-plan ahead of it, overcoming the major challenges in our society, economy, environment, health, and so on. So, what are the common demographic factors? So, here are the big common demographic factors. So, first is gender, educational level, age, location, marital status, religion, language, and nationality. Next recorder, please.